So after this excursion to information theory, we are now going to look at the decoding of some real codes, meaning not of random codes that we have constructed in a kind of Gedankenexperiment, but codes that we encounter. And we're going to use some very simple code to start with, the repetition code. So therefore, we ask ourselves the question, are repetition codes useful? And therefore, we look again at maximum likelihood decoding of the repetition code. We start with specifically over the binary symmetric channel. So we start with the transmission of an, here's a small typo on the slide, so I can cross out this word. So you consider the transmission of an N2 repetition code, so it has two code words, and each information bit is repeated n times. And we consider transmission of our binary symmetric channel with error probability delta. So the repetition code has a minimum distance of n, which means it can correct n minus 1 divided by 2 errors. We have one information bit, which we call u. And we have n code bits, which we denote x1, x2 up to x sub n. And we use an encoding where x1 or xi is equal to u. We just take u and then we repeat it n times. So now we assume that the received vector y contains gamma 0 zeros and gamma 1 ones. So we have gamma 0 zeros and gamma 1, which is n minus gamma 0 ones. Now we can calculate the distance of y to the two code words. And if we recall the maximum likelihood decoder over the binary symmetric channel, we know that the maximum likelihood decoder selects the code word which has the smallest Hamming distance to the received word y. So we calculate the distance of the received word y to the two transmitted code words. So the distance of the zero code word y is equal to the number of ones in y. It's gamma 1, so this n minus gamma 0. And the distance between the 1 vector and y is the number of zeros in y. That's equal to gamma 0. So gamma 1 and gamma 0 denote the distance between y and the two possible code words. So now, if gamma 0 is larger than gamma 1, and we assume that we have an odd n, that makes the most sense because then we can correct the maximum number of errors because we don't have any rounding issue in the Gaussian parenthesis. Then that means the distance of the 1 vector to y is larger than the distance of the 0 vector to y. So it means we decode u hat is equal to 0. Because this guy has a smaller minimum distance. That's the maximum likelihood. On the other hand, if gamma 1 is larger than gamma 0, then the distance of the 1 vector to y is smaller or equal than the distance of the 0 vector to y. And in this case, we have a u hat which is equal to 1. This decoder is called a majority decoder because we count the number of zeros, we count the number of ones, and then we pick the code word with the largest number of zeros or the largest number of ones. We can do this for an example. We can essentially, for n equals 3, we can enumerate all the code words. That's what we did here. And we can just count gamma 0, gamma 1, and we do a decoding. And we see that if there are more zeros than ones, we'll decode to a 0. If there are more ones than zeros, like in this case, we decode to a 1. And here also we decode to 1. So that's the maximum likelihood decoder. That's the decoder that minimizes the error probability on the binary symmetric channel. So that was easy. We can illustrate this with an example. So here is an example with n equals 3. And we have a channel that has an error probability of 0.1. So we have our input U, and what we do is we just repeat every bit in U 3 times. And we arrange it such that the image is not distorted. So each pixel of this image is a bit. Then we repeat this bit 3 times. Here, here, and here. Then we transmit over the channel where 10% of the bits are being flipped. Then we get this noisy version of the image. And then we decode using the majority decoder. And we can see that the errors are clearly reduced. We are not able to recover all the errors. We still that there are a lot of errors that persist in this image, but most of the errors are actually removed or significantly reduced compared to this image. So that's an illustration of the repetition code in the binary symmetric channel. We can now calculate the probability of error. And this is also quite easy. When do we make an error? Well, if more than n divided by 2 bit flips occur, then we will make a wrong decision. Then we file out of this decoding sphere. So imagine we have these 2 code words. We have x1 equals 0, 0, 0. We have x2 equals 1, 1, 1, possibly even extended. And then we put 2 spheres around this. The radius of these spheres is n divided by 2, n divided by 2. The radius of these spheres is n minus 1 divided by 2, this, and n minus 1 divided by 2. And these spheres are not overlapping. But if we make more than n minus 1 divided by 2 errors, then we jump into the wrong sphere. And then we have an error. So we can calculate the probability that this happens. So the number of errors that we can correct is e n minus 1 divided by 2. And we just calculate the probability that more than e errors happen. So that's the sum from e plus 1 to n. And then just the probability that in a code word of length n, more than we have I positions that are flipped with probability delta, and the remaining the remaining n minus I positions are not flipped, which happens with probability 1 minus delta, binomial distribution. We can also alternatively say that this is 1 minus the probability that we make no error, so that we flip less than or equal to those number of bits. And that is given by this expression. So just 1 minus the sum from 0 to minus 1 divided by 2. And then we have the same binomial distribution. And we also have a Jupyter notebook where we can take a look at what is going on in that case. So I can just start the Jupyter notebook and see if I can immediately jump to the right window. It's over here. Perfect. So again, this is just a way of plotting these things. And what we see here is the following. And we can plot the error performance, probability that we make an error on deciding U, as a function of the channel, or the binary symmetric channel. And we can plot this also, we can assume the channel is actually a binary input AWGN channel with hard decision. So it means that delta is coming from the hard decision of an AWGN channel with binary inputs. Then we know that delta is equal to 1/2 times complementary error function of square root of ES over n0, or the Q function of square root of 2 times ES over n0. And then we can calculate those type of curves. And this is what we're also going to see in the script. So this is just a way of plotting these curves. And we can go back to our lecture notes because there we have the final curves as well. So this is just for illustrating. If you want to replicate those graphs, you can take a look at notebook. So this is what we get. First, as a function of ES over n0, we calculate delta, because we know that delta is equal to Q times square root of 2 times ES over n0. And then we calculate the performance for different numbers of n. So we start with n equals 3, and we go up to n equals 19. And we see that the performance improves if we increase n, which makes sense because we have a larger repetition code, and we can potentially correct more errors if we increase n. Now we can also plot the same curves, taking into account the code rate. So taking into account calculating EB over n0, and recall that EB over n0 is 1 over the rate times ES over n0. In fact, n times ES over n0 because the rate is 1 over n. And so this is quite a big difference. So there's a factor of n, and this is actually quite a huge difference. And what we see is that essentially all the coding gain that we observe here is penalized, and we have no net coding gain. We even have a net coding loss. So it's not, in terms of EB over n0, it's never efficient to use a repetition code because we just waste so much bandwidth or so much energy that it doesn't make sense. So we have essentially a net performance loss here. Okay, so that's a little bit disappointing. So what happens if we now use not binary symmetric channel, but a different channel? Okay, first, before we do this, we can also insert the performance of these curves in the spectral efficiency chart. Also in the notebook, there is a way that's how to do this, or that you can do this automatically. Essentially, it works in the following way. We pick a target bit error rate or target error rate, which is 10 to the power minus 6 in this case. And then we look at what is the performance at 10 to the power minus 6 of a specific code. So let's say n equals 3. We have an ES over n0 of roughly 7 dB approximately. And the rate of the code is n equals 3, means we have a rate of 1. So now how do we insert this in the spectral efficiency chart? Well, we look at n equals 3. So the performance at the target bit error rate, which is given in the title, is at 7 dB roughly. And we have a rate of 1/3, 0.33. So that's where we put the dot. So the y-axis is always the rate of the code, and the x-axis is the ES of n0. So we can see that for a fixed rate, we have a signal to noise ratio penalty. Code of rate 1/3 could operate potentially at an ES of n0 of minus 4 dB if we have the best possible code. So there is a quite big signal to noise ratio penalty that we need to hit. On the other perspective, if we have a channel with a signal to noise ratio of 7 dB, then this is the rate loss that we have. We operate at a rate of 1/3, but we could operate at a rate close to 1 with a better code. So that is the rate loss that we get. These are the two perspectives we can look at this problem, either from signal to noise ratio penalty. This is the very engineering approach, and on the other hand, on the rate loss penalty. So then we can take those dots, and we can also calculate the dB over n0 for each of the points, and then we get these points. And then we see that also here we have this big gap to this region. This plot is a little bit more compact because this one tends towards minus infinity. And this one is more compact because it is saturating at minus 1.59 dB in this case. So that's a little bit better for plotting something in a box. That's one of the advantages of this type of plot as well. So now let's take a look at the binary symmetric channel per se. We can also draw a spectral efficiency chart. We have the error probability delta, and we have the capacity. We know that the capacity limit is equal to 1 minus binary entropy function of delta. And we can plot the performance of the codes as a function of delta also. And we see that there's also a very, very big gap with the capacity limit in this case. And this is another description of the code. So here we show the repetition codes of the binary symmetric channel with a fixed delta. So now we fixed delta be equal to 10%. And now we look at the error probability of the codes as a function of the rate. So we construct multiple codes, rate with n going from 1 to 61. And we get the error probability, and we see that this is the curve that we get. And we can also calculate the capacity limit, which is given by this curve. So we see also there is a quite big difference compared to the repetition codes, compared to the capacity limit and the repetition codes. So now we're looking at the soft decision decoding, which means we don't make a hard decision at the output of the channel anymore. We use the full channel output. We have a binary input AWGN channel. And we start with the general maximum likelihood decision rule. So we have U hat is equal to the correlation, the maximum correlation of the received word and the BPSK code words, BPSK modulated code words. So we calculate this correlation. We calculate it for every possible code word. We have two code words, so x0, x1, and we insert x0 and x1 here. This is either always +1 or either always -1. So essentially, we maximize over the sum of yt and minus the sum of yt. And if the sum of yt is larger than the sum of minus yt, then we decode for x0. We decode for the 0. If the sum of yt is smaller than the sum of minus yt, then we decode for x1. So what does it mean if the sum of yt is larger than minus the sum of yt? Well, we can add the sum of yt on both sides. So it means that 2 times the sum of yt is larger than 0 and divide by 2. So it means that the sum of yt is larger than 0. So that's an equivalent statement. So if the sum of all the received values is larger than 0, we decode to a 0. And otherwise, we decode to a 1. Then it means the sum of yt is smaller than 0, smaller or equal than 0. That's the maximum likelihood decoder on the binary input AWGN channel. So we can also calculate the performance of that one. And in order to do this, we assume that we transmit 0 code word. So just without loss of generality, we pick a code word and we calculate the probability that we make an error. And we can easily show that this probability of error does not depend on the code word that we send, so we can just pick one code word. Then we have additive white Gaussian noise. So it means what we transmit, yt is equal to xt plus nt. xt is minus, or is actually equal to, let's write it in this way. So it's equal to minus 1 to the power xt plus nt. And xt is equal to 0. So this is equal to 1 plus nt. So it's a noise nt on which we add 1. So we can say that yt is a Gaussian random variable. It has a probability density function that is Gaussian with mean plus 1 and variance sigma n squared. And now we calculate at the receiver, we calculate the sum of the yt's. We calculate capital Y, the sum from t equals 1 to n yt. This is a sum of Gaussian random variables. And now we have some theory on the sum of Gaussian random variables. So we know that if we take the sum of a Gaussian random variable Rv with mean mu1, sigma 1 squared, and another Gaussian random variable with mean mu2 and variance sigma 2 squared, we get another Gaussian random variable with the mean that is the sum of the two means, mu1 plus mu2, and the variance is the sum of the two variants. And here we should, this should be a statistically independent. Of course, the two random variables, they must be independent, but because we assume the noise realizations are independent, this is true in our case. So we have a RV random variable y. Y is the sum of the yt's, and now we can just take always the two yt's and apply this theorem, and then this will add up to a mean. We have y as a mean of n and a variance of n times sigma n squared. So we have, we build this sum. We have a mean n, variance n times sigma n squared. And now we would like to know what is the probability that y is negative. Because if y is negative, we will decide to a 1. Not to 0. That means we will make a decoding error. Random Gaussian distribution. What is the probability that it is negative? This is something that we can easily calculate. And this is what we are going to do. That gives us our error probability. So probability to decode minus 1 is the probability that y is smaller than 0, smaller or equal than 0. And this is just the sum over the integral over the Gaussian PDF with aforementioned parameters. So we have a mean of n and a variance of n times sigma n squared. And then we can do some calculation and we can express this in terms of either the Q function or here in terms of the complementary error function. It's 1/2 times the complementary error function of square root of n times ES over n0. So you can actually calculate this value of making a decoding error analytically, semi-analytically, because we need the complementary error function, which is tabulated. And this is what we can then plot this. So we have the performance for the binary symmetric channel, and we have the performance for the binary input AWGN channel. And we see that there is a gap between the two curves, and this gap is quite significant. So it's 1 to 2 dB roughly. So we have a performance improvement by using the full channel output without making the decision. This is clear because we have seen it in the beginning of the lecture. We have this good noise and we have the bad noise. The good noise actually helps us in improving the performance. So now we take a look at the EB over N0. So we calculate these curves also for EB over N0. We have seen that for the hard decision output, so the binary symmetric channel, we have a net coding loss. So we lose essentially performance. And now where are the curves for the soft case, so for the binary input AW gen channel with soft outputs? They overlap the uncoded curve completely. So they seem to be equal to the performance of uncoded transmission. And that's something that is a little bit unexpected, and that's something that we're going to calculate. So we observe that the net performance is equal to the uncoded transmission. So let's look at what we have in the uncoded transmission. In the uncoded transmission, we have no code, so ES is equal to EB. And the uncoded bit error rate is 1/2 times complementary error function square root of EB over N0. Now we have a coded transmission. We have a code of rate 1 over N. So we know that the error probability of the repetition code is 1/2 times error function square root of N times ES over N0. We replace ES over N0 by EB over N0. So ES over N0 is R times EB over N0. So it's N times R times EB over N0. R is 1 over N. And we see if we insert R equals 1 over N, the N will cancel. And we are ending up with 1/2 error probability, complementary error function of square root of EB over N0, which is equal to the error probability of the uncoded transmission. So we can actually show quite easily that the net performance is equal for repetition codes. So that also concludes the chapter of repetition codes and decoding of some real codes. In the next chapter, we're going to look at a very important class of codes, which are linear codes.